Okay, the recording has started, and welcome everyone. And we continue with the mini course of Professor Nicolau. Please.
Thanks a lot. So let me remind you last result of yesterday, which was the following: that if imagine that you have an inner function with an interior fixed point. So this means that the inner wall fixed point is inside the disk. Then what we show is that harmonic measure is invariant. So this means that the harmonic measure from the point P of the preimage of a set is the same as the harmonic measure of the set. And this holds for any set, for say any measurable set in the unit circle. So in particular, if P is the origin, so for example, if P is the origin, so if S is inner and fixed is the origin, then of course harmonic measure is just Lebesgue measure. Then what we showed was that Lebesgue measure is invariant. So the preimage of a set is precisely the measure of the set. Okay. So, for instance, just to have a picture, so assume that, for instance, if f is just a power of the identity, so f of z, imagine that f of z is z to the n, right, with an integer n, say bigger than 1. Then what happens is that when you have this mapping, right? You have z to the n. So imagine the preimage of an arc. So for instance, this arc E. Well, the preimage of this arc is, of course, from the topological point of view, it's much more complicated. It's just a union of n disjoint arcs. And the length of this disjoint arc, of each of these disjoint arcs, is just the measure of E divided by n, right? So this is what I was meaning, that topologically the preimage can be very complicated, but still the measure is preserved. Okay, so next step is to show that actually not only harmonic measure or Lebesgue measure is preserved by inner functions with an interior fixed point, but also that the corresponding, say, dynamical system is ergodic. So let me recall the definition of ergodic. So if you have, say, a mapping from, say, x to x, and you have a measure, you have a probability measure, or you have a measure on x, a positive measure on x, then we say that T is ergodic. So we say that T mu is ergodic if the following holds. If whenever, I mean, the only sets which are preserved, we call this mu, are the sets of Lebesgue of mu measure 0 or 1. So if this holds, then mu of V must be 0 or 1. So this means that the only sets which are invariant under the mapping T are precisely the sets of 0 measure or total mass. So I'm sorry, here mu is a probability measure, right? A probability measure on X. This identity here means that these two sets coincide in the sense of the measure mu. So this means that these two sets, T minus 1 of V equal to V, holds except for sets of Lebesgue of mu measure equal to 0. So these two sets could be different, but they could differ at most on a set of mu measure equal to 0. Okay. So now, here is the theorem that you have an inner function, which is not an automorphism, and which has an interior fixed point. You have an interior fixed point. Then we already showed that harmonic measure is invariant. But in this theorem, what we're going to show is that the harmonic measure is actually ergodic. Okay? So it has this property that the only sets which are completely invariant are the trivial ones. So let me give you the proof of that in the case where p is equal to 0. Well, when the function fixes the origin. Actually, this is essentially all you need to prove, because if not, what you would do is to replace f by the composition of f with Mobius transformations in such a way that the composition fixes the origin. Okay. So in other words, it's without loss of generality, we can assume that f fixes the origin. Okay, so let's show that then is ergodic. So assume that you have a set E in the circle such that the preimage, such that the set is completely invariant with respect to Lebesgue measure. Okay. So as I said, this means that these two sets, E and F minus 1 of E, can differ at most on a set of Lebesgue measure 0. Okay. Then what recall that we know that this important property, this is by Lesnars lemma, right? That we know this, right? That let me write. We know that if we look to, let me say it that way. This was Lesnars lemma. Okay, so now we are assuming that f minus 1 of E is equal to E almost everywhere. So this means that this is precisely harmonic measure from the point Z of E, okay? So now when you have this identity, from here to here, you can of course iterate this argument. So now what we are going to do is we just iterate, and then iterating, what we get is that the nth iterate, remember that f to the n is the nth iterate, is equal to this. Okay. But now also remember that f was fixed in the origin. So the origin was the Denjoy-Wolff fixed point. So this implies that by the Denjoy-Wolff fixed point theorem, that the iterates, these iterates here, converge uniformly on compacts to the Denjoy-Wolff fixed point, which in this case is the origin. So this means that this tends to 0. But of course, if this tends to 0, then this harmonic measure tends to the Lebesgue measure of E, when n tends to infinity. Well, so at the end, what we have proved is that this harmonic measure, the harmonic measure here, is a constant function, and the constant is precisely the measure of E. So then this harmonic measure is constant, and this is the measure of E for any Z in the disk. But remember, the boundary values of the harmonic measure is precisely the indicator function of the set B. So then what we get is that the indicator function of the set E is the measure of E at almost every point. But the only way this could happen is that the set E has measure 0 or 1, right? So sets of Lebesgue measure 0 satisfy that, and sets of Lebesgue measure 1, but these are the only ones. Okay, so this implies that E has to have needs to have Lebesgue measure 0 or 1, and this proves that the mapping is ergodic. Okay, so at the end, what this theorem says is that when you have an interior fixed point, if you have an inner function with an interior fixed point, you can apply the ergodic theorem. And Birkhofer, the classical ergodic theorem, tells that the temporal means of the iterates converge almost everywhere to the spatial mean of the mapping. So this is the content of my next slide. If you have an inner function, which is not a rotation, which say fixes the origin, then this first part is the ergodic theorem. So it says that whenever you look at the iterates, and you take, well, G is going to be an integrable function in the unit circle. And when you compute the spatial, the temporal means of the iterates, then this converges to the mean of the function G at almost every point in the circle. Okay, so this is the ergodic theorem. So here I have just mentioned two easy consequences of the first part. So assume, for instance, that you take G being the identity. Well, of course, if G is the identity, these temporal means are just the sum of the iterates. And of course, in that case, this integral, okay? So this second part follows from the first part applied to this function G. But this already has a nice geometrical mean. It means the following, right? At almost every point, remember that whenever you have an inner function, the boundary, the function defined at almost every, the function defined in the circle is only defined at almost every point. So you look at a point where this function and all the iterates are defined. And what you do here is you look to the orbit of this point, right? So you look to f of psi, f squared phi. These will be points in the circle. And so on, okay? And what happens is that the mean of this orbit, so the mean of the orbit tends to the origin. Okay, so this means that the orbit is in a certain sense, well spread out all over the circle, so that the sum of all these values tend to the origin, okay? So this is the first application, say, of the Ergodic theorem, the first example. And here is another example, okay? So the second example is assume that you have as G the characteristic function of a set E, okay? Then, of course, in that case, this integral is precisely normalized Lebesgue measure of E. And what about this, right? In that case, well, it's obvious that whenever you have the indicator function of E composed with Fk, this is precisely the characteristic function of F minus K of E. Well, let me write it here. So this is what I mean, that the characteristic function of E composed with Fk is the characteristic function of F minus K of E. So this means that in here, in the Ergodic theorem, when you are computing that, you are just adding characteristic functions of the preimages. So then this means that this sum counts precisely the amount of times up to time n where the iterates lie in the set E. So in this case, the Ergodic theorem tells you that this mean I mean, the proportion of the amount of times the orbit visits the set E tends to normalize Lebesgue measure of E. Okay. So this is very nice, right? It says, for instance, that for almost every point, arcs of double length are visited, say, in proportion the double number of times than arcs of a fixed length. Okay. So this gives you a good and a nice understanding of how the orbits behave in that case when you have an interior fixed point, when f0 is equal to 0. If you have an interior fixed point, which is not the origin, the same result holds. You just need to replace Lebesgue measure by harmonic measure from the fixed point. Okay? I have just stated it for simplicity in the case of functions fixed in the origin. So this is very nice. And also, I guess, opens the path to explore other situations. In particular, what happens when the Denjoy-Wolf fixed point is not inside the unit disk, but it's on the boundary. Okay, so this is the content of my next few slides. So what we now the main goal is to understand well the behavior of the iterates when you have the Denjoy-Wolf fixed point in the boundary. Okay, so this is what we want to do. Right, you have an inner function with a Denjoy-Wolf fixed point in the boundary. You want to understand how the iterates behave. Well, first, a definition. A mapping, say, from the circle into itself is called recurrent if for almost every point in the circle, when you look to the orbit, you approach infinitely often the initial point. So this means the following, right? That you have here the unit circle. You start with a point psi. Then the orbit, of course, visits, well, many other points. But it happens that infinitely often you are close to the point psi. Okay? Well, and here is the nice result by Arancha. So it says the following. You have an inner function, which is not an automorphism, and with the Denjoy-Wolf fixed point, which is in the closed unit disk, as always, has to be. Then you have two alternatives. You look to the sequence of iterates of the origin. And then this sequence of iterates satisfy the Blaschke condition. If this holds, if the iterates of the origin satisfy the Blaschke condition, then it turns out that the Denjoy-Wolf fixed point is in the boundary. And moreover, it also attracts to any other point in the boundary. So this means that for almost every psi in the circle, the iterates, the whole orbit converges to this fixed point P. Okay. So remember that we already knew that if you have the Denjoy-Wolf fixed point, then the iterates converge to this Denjoy-Wolf fixed point uniformly on compacts inside the unit disk. So this tells you that it converges. In that case, if this holds, this does not only hold on, well, in compacts of the unit disk, but also at almost every point in the boundary. Okay. So it's so first part is telling you that under this condition, the point P, the fixed point P, acts as an attractor even in the boundary. However, if the sum of if the orbit of the origin does not satisfy the Blaschke condition, then the map is recurrent. So this means that whenever you can, if you look to an orbit and you start in a given point, then the orbit visits this, well, any neighborhood of this point infinitely often. Okay, so it's like this is a very nice result. I like it a lot, and it's extremely. It describes well, perfectly well, I guess, the behavior of the orbits. Under this condition, the orbit is attracted to the fixed point. Under this condition, the mapping is recurrent. So you visit your starting point infinitely often. Okay. So let me give the proof of that. Okay. So here is the result. So assume that, so this will be A, and this will be B. Okay. So let's look to A. Okay. So we are assuming that the orbit of the origin satisfies the Blaschke condition. But remember that the orbit of the origin has to tend to the Joule fixed point, right? Then, of course, this implies that the modulus of P is equal to 1. And then, so P is in the boundary. So the first part is trivial, right? The point is to show the second part, that P acts as an attractor even in the boundary, okay? So here is what we need to do. We have here the point P, the Joule fixed point. Let's consider an arc. So let I be an open arc. And we need to show that the orbit of almost every point visits the arc I infinitely often. Okay, so this means that we need to show that the measure of this set is 1, right? Because this tells that after a certain number of iterations, you always lie, after a certain number, say n, big N iterations, the orbit always lie on the arc I, okay? So instead of showing that this has measure 1, what we are going to show is that the complement has measure 0. So we need to show that the complement, which is this, has measure equal to 0. And for this, it is sufficient to show, this is a Borel-Cantelli argument, so it is sufficient to show that the sum of the measures of f minus 1 of I is finite. Okay, so this is our goal, to show this. Okay, so let's do that. So we start with the sum of the measures, and we write it as harmonic measures. This is the harmonic measure from the origin of the same set. And let me write the same set in this way. Okay. Well, now we use the invariance of harmonic measure. So this is precisely, here we use Lesnars lemma, right? Okay, so we have this. And now we just use the definition of harmonic measure as a Poisson integral. So this is just the sum over n of the integral outside I of 1 minus fn0 square divided by psi minus fn0 square dn. But remember, P was the Joule fixed point. So this means that these iterates converge to P. On the other hand, the arc I is centered at the point P. So this means that here you are always far away. So this is bounded below. So this quantity is bounded below by a fixed constant, okay, which would depend only on the measure of the arc I. So then what you get is that this is bounded by 1 over c squared, the sum of the numerator, right? And this is finite by assumption. Okay, so this is the assumption, right? That the orbit was a Blaschke sequence. So this proves part A, okay? It's very simple, right? We are just using Lesnars lemma. So now let's look to part B. So in part B, we are assuming that the orbit of the origin does not satisfy the Blaschke condition, okay? And in that case, we need to show that the mapping is recurrent. So this means that for almost every point, if you look to the orbit, then you return close to this point infinitely often, okay? So for that, it is sufficient to show the following, that for any arc, the measure of the set of points in the arc such that the iterates lie in the arc infinitely often, so for infinitely many n, let me write infinitely often, that this is precisely the measure of I. And this should hold for any arc I of the unit circle. Okay, so this is our goal, right? To show that at almost every point of an arc I, the orbit visits this arc infinitely often. Okay, so then consider the following set. Consider something like the complementary. So consider the set F of points in the arc such that the iterates do not lie in the arc for any n. So this is the bad set, right? It's the set where you start in I, but the orbit does not visit I at any time. No? And note that if you look to the complement, so we need to show that these two sets have the same measure. Okay, so let's look to the difference of these sets. So let's look to these. The point in I such that this set, that the orbit visits the arc infinitely often. Okay, so the plan is to show that this set has Lebesgue measure 0. Okay, but this can be written in this nice form. This is just the union of I intersected with f minus k of f. This is clear, right? Because these are points. These are points which, I'm sorry. These are points where are in the arc I, but such that the orbit does not visit the arc I infinitely often. So this means that there is an index in such a way that after this index, the orbit does not visit the arc I. So this is precisely what is written here, right? That there is an orbit, there is an index k, such that after k iterates, you are in the set F, okay? So remember, we need to show that this has Lebesgue measure 0. So for that, is it sufficient to show that this has Lebesgue measure 0? So we need to show that the measure of this set is 0 for any k. Okay, so to show that, observe that these preimages are disjoint. If k is different from j. This is very clear, right? Because this tells you that after k iterates, you lie in the set F. So this means that after k iterates, you never, the orbit does not visit the set I anymore. So if you have two different indexes, one would be bigger than the other. And then this would imply that if you are in the set, you cannot be in that other set, okay? So, okay, so we have a collection of disjoint sets. And so it is clear, since they are disjoint, that the sum of harmonic measures from the origin will be finite, okay? But of course, again, by Lesnars' lemma, this is just the sum of harmonic measures of the iterates. Okay, this is just Lesnars' lemma. And now what we are going to do is we just write this as the Poisson integral. Bounded, I mean, the denominator is bounded by a fixed constant. Okay, so then what you get is something like that: the sum over k of 1 minus fk of 0 times the measure of f. Okay, so we have this estimate, but remember the assumption was that the iterates of the orbit do not satisfy the Blaschke condition. So the assumption is that this sum is infinite. So the only way this could be finite is that the measure of f was equal to 0, okay? Because this is infinite, right? So by assumption, this is infinite. So this implies the measure of f equal to 0. So now, if the measure of f is equal to 0, now we need to show that the measure of the preimage of f is equal to 0. But now the rest is easy, right? Then the measure of the preimage, this is again, well, I'm going to use Lesnars' lemma again. This is harmonic measure from the origin of f minus k of f. And this is, well, by Lesnars' lemma, harmonic measure from fk of 0 of f. But now f has Lebesgue measure 0. So if it has Lebesgue measure 0, since harmonic measure is absolutely continuous with respect to Lebesgue measure, this implies that this has to be 0. And this is what we wanted to prove, right? That this is equal to 0 for any k. So this finishes the proof. Okay. So you have, I mean, for inner functions which have, for inner functions which have the Nicolau fixed point, say, well, in general will be in the disk, you have this dichotomy, right? Either the orbit of the origin satisfies the Blaschke condition or it does not satisfy it. If it satisfies the Blaschke condition, the Nicolau fixed point acts as an attracting fixed point even in the boundary. If the Nicolau fixed point, I'm sorry, if the orbit of the origin does not satisfy the Blaschke condition, then the mapping is recurrent. So, and these two things could happen. I mean, there are, you can build examples where this condition holds and others where this condition holds. And here is a nice refinement by Dering and Magny. So this refinement says the following. Assume that you have an inner function with a de Joa-Wolf fixed point in the boundary, okay? So we are now in the critical case, right? When the de Joa-Wolf fixed point is in the boundary. Then you look to the following. You take an arc containing this de Joa-Wolf fixed point. So here is the de Joa-Wolf fixed point in the boundary. You look to an arc. And now you do the following. You count the number of times the orbit lies in I among the first n elements of the orbit. And you count which proportion of time the orbit lies in I. And what happens is that for almost every psi, this proportion tends to 1. So I like to think on this theorem in the following way. So you may have, it's something like that. You may have, here is the de Joa-Wolf fixed point, okay? So here is P. Here is the arc I. And you start with a point psi. So if the mapping, I mean, if P acts as an attracting fixed point, of course, after a certain number of iterates, you lie inside the arc I and you approach the point P. And this is not very surprising. However, remember that the mapping can be also recurrent. If the mapping is recurrent, this means that if you start at almost every point psi, the orbit visits any neighborhood of psi infinitely often. So the orbit must visit, so this would be f of psi and so on. The orbit should visit should visit psi infinitely often, or any neighborhood of psi infinitely often. However, what the Dering and Magnier result tells you is that even if it has to visit, it has to be close to psi infinitely often, the orbit spends most of its time close to the de Joa-Wolf fixed point. So this means that even if the de Joa-Wolf fixed point, when it's in the boundary, may not be attracting in the boundary, it is attracting in the mean, right? Most of the time you lie inside a neighborhood of the de Joa-Wolf fixed point. So let me tell you how this is proved. And well, here is, this proof is a little bit more sophisticated, and there are 2 steps. You can assume, without loss of generality, you can assume that the mapping is recurrent. Because remember, you only had 2 possibilities. Either the mapping is recurrent or the Joa-Wolf fixed point acts as an attractor. And in that case, this result is trivial, right? If P acts as an attractor, then of course the orbit lies close to P for any big indexes K. So you can assume that the function f is recurrent. In that case, what Dering and Magnier showed was that in that case, you have an invariant measure. And since you have an invariant measure, then what happens is that for almost every psi, this limit exists. So the first part is to show that the limit exists. So I'm going to skip this part. Because it could take, I mean, it's again, the argument is elementary, but it could take me some time to do it, and I prefer to move to another topic. So this is the first step, that the limit exists. But the second is very easy. So let me complete the second step. So now in the second step, you need to show that this limit, which exists at almost every point, is precisely 1. So what you do is the following. Let's look to the integral of this limit. So this limit depends on the function side, on the point psi, right? So it's a function of psi. So you look to this and you integrate with respect to Lebesgue measure. Okay. So then by dominated convergence, this is the limit of the integrals, right? And remember that this is just the characteristic, the sum of the characteristic up to n. This is just the sum up to n of the characteristic functions of f minus k of I. Okay. So what you have here is the limit of the integral. Well, of these measures, right? Which I already write as the harmonic measure from the origin. So these are just the measures of the Lebesgue measure, the normalized Lebesgue measure of f minus k of I. Now we apply again Lesnars lemma, and this is the harmonic measure of fk of 0 the set of the arc I. But remember again, fk of 0, p was the Lebesgue, was the Denjoy-Wald fixed point, so fk of 0 tends to p. Okay, so this is the and I was an arc containing the Denjoy-Wald fixed point. So this means that fk of 0 are very close, are here very close to p. And in that case, of course, this quantity tends to 1. So this quantity here tends to 1. And then you are just averaging numbers which tend to 1. And of course, this limit is 1. Okay. So the second part is very easy. So what we have learned is that even if the mapping is recurrent, so even if P is not an attractor in the unit circle, in the mean acts as an attractor. Okay. Here is another result I wanted to mention, which is again a very nice result by Aranson and Pomerinke, which tells you when the mapping is ergodic, okay, with respect to Lebesgue measure. And this holds, as you see, the mapping, you have an inner function, then the mapping is ergodic with respect to Lebesgue measure, if and only if the pseudo-hyperbolic distances between two different orbits always tend to 0. So this means that the orbit of any 2 points become closer and closer, okay? So for instance, if the mapping F had a Denjoy-Wald fixed point inside the unit disk, then we know that the orbit tends to this Denjoy-Wald fixed point. So then, of course, this would hold, right? We already show that in that case, the mapping is ergodic, okay? But it could still happen that the inner function has the Denjoy-Wald fixed point in the boundary, and still this condition could hold or not hold, okay? Okay, so this is again a nice criterion about dynamical properties of the inner function. Okay, so now this was the first part of the talk today, and in the last 5 minutes, I want to introduce a tool which will be used in the last talk. And this tool has it's really important and very nice. It's what's called Alexandrov-Clark measures. Okay. Let me say that Alexandrov-Clark measures are a topic which was in a notion which was introduced by Clark in the 70s in relation with problems in operator theory. And the main properties of Alexandrov-Clark measures were proved by Ahern, Clark, Sarason, and many others. And they are collected in a couple of nice surveys by one survey by Paul Thoratsky and Saracen, another nice survey by Eero Saxman, and most of their properties are also collected in several textbooks. For instance, in the nice book by Sima, Mattenson, and Ross, and in many other places. So let me start giving you the definition. So if you have an analytic mapping from the disk into itself, and you have a point alpha in the unit circle, what you do is you consider this composition. So you have this mapping from the disk into itself. And then what you do is you just compose it with this Mobius transformation, which maps the unit disk into the right half plane. Okay? Then, of course, you have an analytic map. I mean, the composition is an analytic mapping from the disk which has positive real part. So it can be written as the Herglutz integral. So this is the composition, which can be written as Herglutz integral of a positive measure. And this measure is what's known as the Alexandrov-Clark measure, sometimes called the Clark measure, sometimes called Alexandrov-Clark measure of F at the point alpha. Alpha is a point inside the unit circle. Okay. Well, if you take real parts, then, well, the real part of this is the Herglutz kernel, and it's very easy, just a computation to show that the real part of this kernel is precisely the Poisson kernel. So you get here the Poisson kernel at the point f of z, and you get here the Poisson kernel at the point z. Okay. So here is what I have just said. Okay. So let me give you a few, well, some of the standard properties of these Alexandrov-Clark measures. Well, the first one is that the function is inner. So the function, the function being inner means that the modulus tends to 0. The modulus tends to 1 when you approach the circle at almost every point. When you approach non-tangentially the circle at almost every point. So this means that the function is inner if and only if this tends to 0 when z approaches non-tangentially any point in the unit circle. So this means that f is inner. This is, of course, the Poisson. This is, of course, the Poisson integral. Only if the Poisson integral of mu alpha tends to 0 at almost every point in the circle. But of course, we know that the Poisson integral tends to the derivative of the measure with respect to Lebesgue measure, at least at almost every point. So this should be equal to 0 at almost every point in the circle. So this means that the function is inner if and only if mu alpha is singular with respect to Lebesgue measure. This holds if and only if mu alpha is singular. So inner functions are precisely the ones which have whose Alexandrov-Clark measures are singular. What more? Well, the next thing is that mu alpha is concentrated precisely on the set where the function f is equal to alpha. And this is again easy to show. Actually, mu alpha, since it's singular, mu alpha is concentrated on the set where of point psi, where this derivative with respect to Lebesgue measure is equal to plus infinity. So these are places where the Poisson integral tends to infinity, right? So these are places where this Poisson integral tends to infinity. But of course, this happens. I mean, if this Poisson integral has to tend to infinity, the only way it can be tending to infinity is that this denominator tends to 0. So f of z tends to alpha. So this is contained in the set where f of psi is equal to alpha. Okay. So I guess my time is over. So I guess I prefer to stop here and to start next tomorrow, just recalling the definition of Alexandrov-Clark measures and continuing with their main properties. So thanks a lot.
Thank you. We have time for questions. Oh, if not, then let's thank our speaker again, and we will continue in 8 minutes.
Okay.